big O of n time. But the goal today is, again, constant time. So how might we go about implementing this? Well, the spoiler is that it's going to be called a hash table. But how we actually implement this magical black box is a little more interesting, if non-obvious. So suppose we initially create a data structure using an array of some sort. So we'll call it table, but a table is effectively synonymous now with an array. And suppose that the goal here is to store things like, let's say, people's names in this array. So suppose I want a data structure. We're even more simple than student objects. I just want to store students' names. And then I want to be able to check, is Alice in my black box? Is Bob in the black box? Or have I seen them before and put them into this data structure? I just want to be able to answer those queries. So I propose implicitly here an array, aka table, that's of size 26. And that's not a coincidence. What might the 26 conjure up ideas of here? Yeah, so alphabetical somehow, right? So what if we're given an arbitrary list of names, Alice, Bob, Charlie, and so forth, in random order, though, suppose I want to keep track of whether or not I've seen those names before. Well, where do I put them? Well, I could, every time you hand me a name, I can store it in this black box and just put it at the first available location. I can put it at the bracket 0, bracket 1, bracket 2, bracket 3. But if I insert things into a data structure in random order, what's going to be the running time of search when I ask for that same structure back out? It's going to be big O of n, right? If you do something in random order, and we've seen this multiple times. We saw it when Sean was up here on video on the board just trying to find some number. Well, if you put things in random order, you're just deferring your effort till the end of the process, till you want to get that thing back. So we don't want that. Today, we want constant time, ideally lookups. So as this table suggests, if I hand you Charlie first, rather than put Charlie at the first available location, where might you instead put him? So bracket 0, 1, 2, 3, 4, which one comes to mind? So maybe bracket 2, right? Maybe you should just in advance decide that bracket 0 is going to be for people whose names start with A. Bracket 1 is going to be for people whose names start with B. Bracket 2 is going to be for people whose names start with C. And then people whose names start with Z end up at the end of this array at location 25. But because it's an array, you can get there instantly, right? Using square bracket notation, you have so-called random access to memory, so you can jump right there. So even though it looks like Zeke is getting the short end of the stick by going all the way at the end of the black box, you still have instantaneous insertions. Except if what happens? Right? What if two people have a name that starts with Z? Or maybe more realistically, two people have a name that starts with A or B or some of the more common letters of the English alphabet? Well, now we kind of have a problem. If in advance we only allocated 26 buckets, we can store 26 people, but just statistically, a class of 26 students is not going to have unique starts of everyone's name. So what could we do, just instinctively? Suppose I insert Charlie, and he goes to bracket 2, and then Chuck comes along, and I need to insert him as well. Where do we put Chuck, whose name obviously starts with C as well? OK, so maybe a 2D array, right? So that's actually not a bad idea. So maybe instead of allocating a 1D array, I could allocate a 2D array and then just put Charlie there first and then put Chuck to the right of him conceptually. We start drawing this as a grid. All right, but then Carmen comes along. And so now we have a third C name. And what do we do with Carmen? So right, we have a 2 times 3D array. So we need another dimension. So this is not a bad idea, right? If you need to be able to insert more people into the array, well, just kind of increase your number of dimensions so that you can have people vertically, so to speak, and also horizontally. But the problem there is every time we double the dimensions from 1 by n to 2 by n, well, now I'm allocating effectively more space for Z names and Y names and Q names, and we're probably not going to have that many of them. So there's a downside there. If we use arrays, or 2-dimensional or 3-dimensional arrays, no less, we're kind of wasting space on the less common letters, but even though we're solving problems for the least common, for the more common letters. So what about this? Why don't we try to leverage this reality statistically that there's not that many people whose name starts with Q or Z. My apologies statistically to those whose names do start with Q or Z here. But suppose that we're willing to accept that for small data sizes, we're not going to get someone with the Q name or the Z or a few other letters as well. So what if I first try to go to bracket 2 and I try to insert Charlie there and I get some kind of collision? well, why don't I just, well, if bracket 2 is busy, well, let me put it in bracket 3 or bracket 4. In other words, just start probing the array, so to speak, from top to bottom. And the first available spot below Charlie is where you can put this other C name. So does this work? Does this not work? Well, it definitely makes more efficient use of the space, right? Because now, if we have 26 buckets, we're going to fill all of them at some point, even if not everyone is exactly where we would like them to be. But in the worst case, what's going to happen here? What's going to be the worst case lookup time for Alice if Alice just so happens to be inserted last, number 26 in the class, and there's already someone else with the letter A as their name? Yeah, it's going to take us big O of n again to get to Alice. So not ideal, right? Because Alice might get arbitrarily put at the end of the array, and just finding her, again, this is kind of now devolving back into random order. And random is typically bad, at least in terms of running time here. So maybe this isn't such a big deal, right? I'm kind of making up these names. I don't even know where Carmen came from off the top of my head. So maybe this idea of collisions is not all that likely. Well, we can actually answer this question. If you assume a room full of, say, n of us, n CS50 students, what's the probability that 2 students here are going to have the same birthday, right? This is kind of the same question. There's 365 or 66 days in the year, and that's a finite number. There's a finite number of us, less so than on some days. And you presumably, if we have 367 students here today or earlier in the semester, then there's got to be a collision, right? This is what's called the pigeonhole principle. For more on this, take CS 121. So we could do this. Actually, we could probably spend like 20 minutes trying to figure out who has the same birthdays here. But this could actually very quickly devolve into a big mess. But let's assume that this is probable. Let's actually see if we can't slap a number on this. So this is just a formula that actually answers the other question. What's the probability that every one of us has a different birthday? Well, this is actually a little easier to compute, and we can do it as follows. If I pick one person out of the audience, what's the probability that you have a different birthday than everyone else at this point in time? 100%, because I haven't considered anyone else. So that's 100%. That's 1 over 1, hence the 1 in this formula. Now I move on to the second student in the room. Well, she can have any possible birthday out of 364 days, because already one day was taken by someone else. So if we want the probability that these 2 students do not have the same birthdays, we do 100% times like 99%, give or take, otherwise known as 1 minus 1 over 365. And that just gives us the probability at this point in the story that these 2 have different birthdays. And then we keep multiplying, we keep multiplying, we keep multiplying. And if you actually do all this out, or look at the back of like a physics or a math book, you get this formula, which at first glance, admittedly, is not all that enlightening. You're probably not graphing this mentally in your head all that quickly. But if we do actually graph not this, but 1 minus this, because recall that the question was, what's the probability of a collision? Right now, this is the probability of no collisions. I want to know if we're going to start talking about hash tables and using arrays and have to deal with multiple C names or A names or B names, how likely is that? Well, as the birthday problem suggests, it's actually really, really likely. So this is a plot whereby the x-axis represents number of students in the room, or number of birthdays, equivalently. The y-axis represents the probability of a collision of 2 people having the same birthday. And what's remarkable about this is that as soon as you get to a class full of like 49, 52, 58 students, give or take, there is a nearly 100% probability, even in a class that's much smaller than CS50, a class of just 50 students, that there's going to be a collision. And that's thanks to combinatorics and just the probability of someone actually having the same birthday as someone else. So what's the takeaway here? Well, even if you scroll back, this is kind of remarkable. Even in a class of like 28 students, which is much smaller, there's like a 60 or 70% chance of 2 people having the same birthdays. Now, again, what's the takeaway here? Well, if we now generalize this to the problem of data structures and this thing called apparently a hash table, we might assume that we're not going to have Q names or Z names. This is not really a big deal. We're not going to have collisions. But indeed we are. Even if we scale down to 26 people, 26 names, the probability of a collision, 2 people having the same birthday, or if we assume a uniform distribution of names, the probability of 2 people in a 26 student class is 60%. So in short, this is a problem. So it's not safe to sort of sweep this detail under the rug and just hope that, what are the odds that this happens? In fact, it's very often going to devolve into a situation where our lookups are big O of n. And the whole goal here is to avoid that. So I used this buzzword a moment ago, linear probing, to actually start somewhere in the array and then just kind of probe for an open available space if you want to insert something into this array, like a student or a number, and its ideal location is already occupied. But we already discussed ultimately the downside. In the very worst case, and that's generally what big O notation conjures up, in the very worst case, we might just insert Alice into this data structure last. There was already someone else like Adam with a name who starts with A, and there was a Bob and a Charlie and everyone else. So the very last Alice gets stuck all the way at the end of the data structure, which means when I say, hi, is Alice in this list? And I ask the black box, it's going to take it linear time, big O of n, and literally n steps to confirm or deny the answer to that question. So not ideal, but very efficient use of space. But what's it costing us? Time. So there again is this trade-off. So rather than just do a two-dimensional array, why don't we steal what we talked about Monday and start to merge these two ideas? So this thing here is a hash table, but it's a little fancier looking in that what we really store vertically, so to speak, is still an array. But this time, it's not an array of numbers. It's not an array of strings. It's just an array of pointers. Because pointers, recall, can point to dynamically allocated data structures, whereby you don't know in advance how much memory you're going to need or how many structures you're going to need. So why even pre-commit? We can just decide initially, in this case, this is related to a birthday scenario. So in this case, I have an array of size 31. It just, because of the textbook that we scanned this from, it's not 0 index, but that's fine. There's 31 pointers. And each of these now represents this idea of a birthday in a given month. What is the who has a birth date of like January 1 or February 1? Well, that person might go here. Or something 31 will go here, or 27, 26, and so forth. So we only allocate a bunch of pointers. So our table, in this case, is not size 26 anymore. It's size 31, but it's still finite. But what we have now is the ability to grow laterally. So I think the example that this author used was famous people. I think that might be Sam Adams up top. So Sam Adams has a birthday, I think, unless I'm making this up, of something 2 in the month. And so he was inserted there. So what does it mean now to insert into this data structure? We're not just plopping him or her into a pre-existing array. What kind of code do we have to write to insert S. Adams into this data structure? What functions do we need to call if we implemented this in C? It's related to memory. It's related to allocation. Malloc. OK. Actually, I think it was funny. I think we saw in the quiz function calls like mallocate. That was one. And yeah, there were some other funny ones. I'll keep to myself.